Hi, good morning. Hope all of you are fine. Today we are going to start our next section, session 3.5, linear functionals. Okay, now what do you mean by a linear functionals? Just to recall the definition of a linear transformation. Okay, now what do you mean by a linear functional? If V is a vector space over the field F, a linear transformation F from V into the scalar field F is called a linear functional on V. Okay, so a linear functional is actually a linear transformation from V into a scalar field F. Okay, so this f must satisfies f is a function from v into f and f satisfies the linearity property. F of c alpha plus beta equal to c into f of alpha plus f of beta for every alpha comma beta belongs to v and for every c belongs to f. Okay. Now we move to some examples. Now let F be a field and let A1, A2, etc. A and B scalars in F. Now define a function F on Fn by f of x1, x2, etc. xn is equal to a1 x1 plus a2 x2 plus etc. plus an xn. Then f is a linear functional on Fn. Okay, and we are defining like this. Suppose if you take r, this is of the form, what will be the function f from r to r defined by f of x is equal to some cx. Now suppose we are defining f from r2 to r, f of x1 x2 which is equal to some a1 x1 plus a2 x2, and the general form is this one, a1 x1 plus a2. Clearly you can easily verify on this one. This is actually sum of linear combination x1 x2 etc xn. Okay, therefore f is a linear functional on fn. Now what is this f of f of e1, f of 1 0 0 etc 0, this is a1. Okay, therefore this f you can write as a1 is f of e1. Therefore this you can write as f of e1 x1 plus f of e2 x2 plus etc plus f of en xn. Okay, just uh, note that also. Now every linear functional on Fn must be of this form. You must note this. Every linear functional on Fn must be of the form f of x1, x2, etc. xn is equal to a1 x1 plus etc plus a2. Suppose you are to ask question like this. Write any linear functional on R3. You can write f of x1, x2, x3 is equal to, when you don't write a1 x1 plus etc, you can put some values for a's. Some 2x1 plus 5x2 plus 6x3. This is enough. Okay, this is a linear functional on R3. Similarly, you can write anything. Okay, so any linear functional on Fn must be of this form. Now move to another example. Consider the space of n by n matrices Fn by n and let A belongs to Fn by n. Then trace of A is defined by the sum of diagonal elements of A. Okay, if A is like this, then the sum of diagonal entries is called trace of A. trace of A equal to A11 plus A22 plus etc. plus ANN, and the next result says that trace function is a linear functional on Fn by n. That means we have to clearly trace this is a sum of elements in Fm, F again element in F. Okay, these are elements in F. Now, what is trace of CA plus B? For a matrix CA plus B, ijth entry of CA plus B is same as C into ijth entry of A plus ijth entry of B. Therefore, this is same as CA11 plus B11 plus CA22 plus B22 etc. plus CANN plus BNN. And take C outside, write like this, and this is equal to trace of A plus trace of B. Therefore, trace function is a linear function on Fn by n. Okay. Now let V be the space of all polynomial functions and T be any element. That means that is the set of all polynomials. And we define LT of P equal to PT, the value of polynomial at the point T. Then we can easily show that this LT is also a linear function. It is very easy. You take some two function, some CP plus Q, and clearly this is CP plus Q of T, and this is same as CP of T plus Q of T, and this is same as C into P of T plus Q of T, and this is same as C into LT of P plus LT of Q. This implies LT is linear. Now moving to next example, consider closed interval AB and CAB the space of all continuous real valued function. Then LG we define integral A to B G of T dt. As G is continuous, we can define integral, and this is also a linear function. You can easily verify. Okay, sum of continuous function again continuous, therefore integral is defined and you can write. Okay. Now, if you consider the vector space V and consider the collection of all linear functions on V, that again form a vector space. Okay, and we denoting this as V star. Okay, as collection of all linear transformations form a vector space. What is about a collection of all linear transformation? LVW. We have already discussed LVW. This is collection of all linear transformation from V to W, and this form a vector space. Here set of all linear transformation from V to F. Therefore, this also form a vector space, and this space is we are denoting this as V star, and it is called dual space of V. Okay, collection of all linear functionals is denoted as V star. Now we are going to prove dimension of V star is same as dimension of V. This is actually dimension of V star. Okay, dimension of V star is same as dimension of LVF. Dimension of LVW is same as dimension of V into dimension of W. Therefore, here dimension of V into dimension of F and dimension of V into 1, because dimension of a field is 1. Okay. Therefore, if you consider R, what about dimension of R? Singleton set 1 form a basis. Okay. Therefore, in general, F singleton 1 form a basis. Therefore, dimension of F is 1. Therefore, dimension of V into N, which is equal to dimension of V. This implies dimension of V star equal to dimension of V. Now we are going to prove one theorem, and this theorem is very important. Okay. Listen carefully. Let V be a finite dimensional vector space over the field F. Clear? V is a finite dimensional vector space over the field F, and let B equal to alpha 1, alpha 2, etc. alpha n be a basis for V. Okay. Then the theorem says that there is a unique, okay, dual basis. Okay, B star equal to F1, F2, etc. Fn for V star such that Fi of alpha j equal to delta ij. Okay, that means for alpha 1, alpha 2, etc. alpha n, you can find a F1, F2, etc. Fn such that Fi satisfies this condition, and this form a basis for V star. Okay, now All these things are very easy. For each linear functional f on V, we have f equal to sigma I equal to 1 to n f of alpha I into fi. You have to remember this definition. And for each vector alpha in V, we have alpha equal to sigma I equal to 1 to n fi of alpha into alpha I. So you have to remember this. F is a F in terms of linear combination Fi. F is equal to sigma I equal to 1 to n and its coefficient is F of alpha I. Okay. Once again, F is equal to F is a Fi's are basis, therefore F is a linear combination of Fi. Therefore F is equal to sigma I equal to 1 to n F of alpha I into Fi. Similarly, alpha is our basis, therefore alpha is a linear combination of alpha I and its coefficient is fi of alpha. Therefore, alpha equal to sigma I equal to 1 to n fi of alpha into alpha I. Okay. Just again repeat the statement for f and alpha. These two definitions are very important. If fi's are dual basis, then f equal to sigma I equal to 1 to n f of alpha I into fi and alpha equal to sigma I equal to 1 to n fi of alpha into alpha I. Okay. Now we will move to the proof. Here we have to show that B star is equal to F1, F2, etc. Fn is a basis for B star. Okay. This Fi satisfies the condition. Fi of alpha j is equal to F satisfies the condition. Fi of alpha j equal to delta ij. Now what is the meaning of that? Fi of alpha. Fi of alpha j equal to 1 if I equal to j, 0 otherwise. Okay, that is the definition of Fi of alpha j. Now we have to prove this form a basis. Now what about the number of elements in this set? N. What about the dimension of V star? N. Because dimension of V is here this form a basis for V. Therefore dimension of V is here number of elements is N. Dimension of Vn and therefore dimension of V star must be N. Here number of elements is n. Therefore, to prove this form a basis, it is enough to prove that this set is linearly independent. Okay. For this, suppose C1, let C1, C2, etc. Cn belongs to F such that C1 F1 plus C2 F2 plus etc. plus Cn Fn equal to 0. All these are function linear combination of function equal to 0 means this is equal to some 0 function. Okay. Here actually 0 functional. Okay. Now, this is this of alpha j equal to 0 of alpha j. Some f equal to g implies f of alpha equal to g. Now, c1 f1 plus c2 f2 plus etc. plus cn fn equal to 0 implies this. We have this result. F equal to g implies f of alpha equal to g of alpha for every alpha belongs to v. And therefore, it is true for f of alpha j equal to g of alpha j. Okay, because alpha j belongs to V. Therefore, we have this result. We have this result 0 of alpha j equal to 0. Therefore, here we have f1 of fi of alpha j equal to 1 if I equal to j. Okay, therefore here I and here 1 and j therefore different, therefore 0. 2 and j therefore 0. Again, if you reach Cj, this is actually Cj Fj of alpha j. Therefore, Cj into 1 plus etc. plus Cn into 0. Therefore, finally, we get Cj equal to 0. Therefore, if we take alpha j, we get Cj equal to 0. If we take alpha 1, we get C1 equal to 0. If we take alpha 2, we get C2 equal to 0, etc. If we take alpha n, we get Cn equal to 0. Okay. If j is arbitrary, we get C1 etc. plus Cn equal to 0 implies Ci equal to 0 for every I. This implies that set is linearly independent. Now we have to prove uniqueness. Suppose G1, G2, etc. Gn be any other basis for V star such that this condition holds, and we have to prove that Gi equal to Fi for every I equal to 1 to n, etc. This is very easy. We have to prove Gi of alpha equal to Fi of alpha for every alpha belongs to V. So for every alpha belongs to V and alpha you can write like this. Now fi of alpha equal to fi of this one and fi of this one. I'm skipping all this step, and this is equal to Ci into 1 plus etc. This implies Ci. Therefore, Fi of alpha equal to Ci. And Gi of alpha, same process repeating, and we get Gi of alpha equal to Ci. Fi of alpha equal to Gi of alpha. This implies Fi equal to Gi for every I equal to 1 to n. This implies the representation is unique. Now from equation 1, what we get? If you take any alpha belongs to V and alpha equal to this one implies Fi of alpha equal to Ci. Therefore, once again, Fi of alpha equal to Ci. Therefore, if alpha equal to this one, then you can write Fi of alpha equal to Ci implies F1 of alpha for C1, F2 of alpha for C2, etc. Fn of alpha. Okay. Therefore, alpha you can write as sigma I equal to 1 to n Fi of alpha into alpha I. Okay. Clear? Now, last step. Suppose f belongs to V star, then as f1, f2, etc. Fn is a basis f, you can write as linear combination of f1, f2, etc. Fn. Now, f of alpha I equal to this of alpha I, and that's equal to this of alpha I, this of alpha I, etc. Cn of alpha I. Fi of alpha I is 1 for all other i's, that is 0. Therefore, this is Ci. Thus, we get Ci equal to f of alpha I, and replace here f is equal to this f you can write as sigma I equal to 1 to n Ci Fi, and for Ci you can replace f of alpha I into Fi. Therefore, f is equal to sigma I equal to 1 to n f of alpha I into Fi. Okay. So this is our theorem. That means given any alpha 1, alpha 2, etc. alpha n, there exists a unique dual basis. That basis is called dual basis f1, f2, etc. fn, which satisfies the condition fi of alpha j equal to delta ij. Also f equal to sigma I equal to 1 to n f of alpha into fi, and alpha equal to sigma I equal to 1 to n fi of alpha into alpha I. Okay. And there is one homework. Give a linear functional on R2. You can easily solve this problem. Okay, that's all for today's class. In the next class, we will discuss some problems.